Thank you so much for allowing me to talk to you guys today. Today I'm going to be talking about some recent ongoing and upcoming work kind of at the intersection of machine learning techniques and hydrodynamical simulations. So essentially trying to figure out how to build models that combine both these elements together to infer cosmic parameters and astrophysical parameters that are both robust as well as can capture kind of the full variety of the physics we could model. So to motivate this a little bit, I was trained kind of originally as a cosmologist, and from that standpoint, kind of the picture we view when we're trying to do, for example, galaxy clustering surveys or modeling things like TSZ or other large-scale structure probes, is we have some initial conditions, some initial Gaussian random fields, where we want to infer the parameters that define these initial conditions, this Gaussian random field. We evolve it forward to some dark matter structure. Of course, though, we can't see the dark matter structure, so we look at biased tracers. We apply some nonlinear transformation on the dark matter field to get some galaxies or some gas. And so this kind of assumes there's some relationship between the late time dark matter structure and the galaxies. And this seems to be quite true on large scales. But when we really try to dive into smaller and smaller scales, if you're really trying to pick apart the astrophysical systematics that could be affecting our cosmological probes, we realize this relationship is quite complex. And to really model the full variety of galaxies that we see, the full variety of gas properties that we see, we really need to treat this all as an integrated system. We really need to understand how the gas is evolving over time, how galaxies form over time, what their assembly bias properties are, things like that. And so we really have to view this all as an integrated structure, and try to disentangle all these kinds of exotic physics that we might want to pick out of it, the things that we're really trying to constrain in modern cosmology. And this is where machine learning techniques as well as advanced simulation techniques come in to try and understand each of these components and try to figure out where the data that we see today, what physics is underlying it, what physics is driving it. So for the first part of the talk, I'll motivate this a little bit more and trying to figure out kind of cases where this dark matter to baryon mapping breaks down and where it seems like we need to insert additional understanding, and we need to, where understanding the astrophysics is quite important, including from Lyman-alpha Forest, as well as from the thermal Sonev-Zeldovich effect at lower redshift. We'll then talk about cosmological hydrodynamical simulations, what elements go into them. And then kind of in the second part of the talk, I'll discuss how machine learning is kind of a new paradigm for understanding these things, and how machine learning combined with hydrodynamical simulations can open up whole new kind of avenues for cosmological inference, go beyond standard summary statistics and look at things on the field level, try to include joint estimation of both cosmological and astrophysical parameters, propagating through the uncertainties. So Lyman-alpha Forest. So Lyman-alpha Forest is a quite common cosmological probe. It was first kind of discovered in the 1960s when they noticed that high redshift quasars, quasars above redshift 2 or so, had all these absorption lines, redward of the Lyman-alpha peak. And so, meanwhile, lower redshift quasars did not contain these absorption lines. And this relates to the fact that at higher redshift, there's more neutral hydrogen along the line of sight, and so you can actually pick up these absorption lines. And I think the video is broken, but essentially how it works is that as the quasar light passes through the intergalactic medium on its way to us, the whole spectra is slowly getting redshifted by cosmological redshift. And as it gets redshifted, it passes through additional neutral hydrogen in the cosmic structure, and that shows up as absorptions. The light at the Lyman-alpha frequency will get absorbed. And so as this whole thing moves across, you essentially pick up you can construct a one-dimensional line of sight of the neutral hydrogen gas. And if we relate this neutral hydrogen gas to the dark matter structure, we can use the Lyman-alpha Forest as a cosmological probe. We can understand how matter is clustering at high redshift and use that information to constrain cosmological models. So kind of one of the first notable cases of this was using it to constrain warm dark matter models. And then more recently, it's a major component of DESI and earlier BOSS to constrain cosmic evolution over time. But again, this assumes that we kind of understand the mapping between the neutral hydrogen and the underlying matter fields we're reconstructing. So a different way to kind of look at Lyman alpha forest and use it as a cosmological probe or an astrophysical probe is to instead try to reconstruct the three-dimensional density. So one line of sight gives you a one-dimensional density, when we could try to essentially play a high-dimensional connecting the dots game to construct a three-dimensional map of the Lyman alpha forest. And this is the idea behind Lyman alpha tomography. So you can imagine if here's just from a simulation, we have some cosmic structure. This is the neutral hydrogen in redshift space from a hydrodynamical simulation. You can see, by eye, there's a large void, a big cluster, some filamentary structures connecting the clusters. And so you can imagine if we had a grid of background sightlines, here, perfectly spaced because we're in a simulation, but a grid of background Lyman alpha, a grid of background quasars, or other background sources that have a continuum where you can see these absorption signals. If we look at the spectra of all these lines of sight, you lay them down on a piece of paper even, you can just see by eye the cosmic structures. Where there's absorption, you can connect the dots and trace out this structure. And so this is the idea of Lyman alpha tomography. And this was first done back in 2016, and now more recently we created a large map in 2023 of one particular patch in the sky in the cosmos field. So this is where there's a lot of observations, a lot of spectra have already been taken. We have a good we know which background sources to target. And we found 320 background sources. So these are a few quasars as well as, again, these galaxies with continuum emission. And we could, you can plot them on 2D and see their distribution. But the most important thing is that they have this third dimension along the line of sight. We have these absorption lines. We can actually reconstruct three-dimensional maps of the Lyman alpha forest and of the neutral hydrogen. And so I think the video is also broken, but over here there's a large void. I think this is the largest cosmic void, the highest redshift cosmic void discovered still to date, as well as all these clusters and the filamentary structures between them. And so this provides a unique view of the high redshift universe where we're able to reconstruct the cosmic web at roughly a 1 megaparsec resolution. But when we dive a little bit deeper and we wanted to say, well, does this Lyman alpha absorption really directly connect to the underlying dark matter field? The story becomes a bit more muddled, particularly when we look at high redshift clusters. So here is one cluster. So if we first look at these dots here, over here is a big cluster of galaxies. I think this was found by the Z-Fire survey. And we look at the observed hydrogen absorption in the same field. We notice that there's not actually a particularly large absorption over here. If we just try to map directly the neutral hydrogen to the underlying density field, in this particular region of the high density, it doesn't quite work as you would expect. Meanwhile, in less dense regions, in regions that are more dominated by the diffuse gas component of the high redshift universe, we see this mapping works much better, that the galaxies seem to trace the same underlying distribution as the neutral hydrogen is tracing. And so the kind of question comes up is, well, what's driving this? Why, in these dense cosmic environments, does the neutral hydrogen not seem to be a good probe of the underlying density field? And the current idea, although we're going to try to study it more with the upcoming prime focus spectrograph survey, is that feedback seems to be really driving a lot of the thermal evolution of the gas at these high redshifts in these massive clusters. There must be a very powerful additional energy source driving the heating of the gas and affecting the neutral hydrogen. So this could be from supernova, it could be from star formation. We think it's perhaps more likely driven by AGN formation, but again, we're trying to pick that apart in next generation surveys. And so going to low redshift, we can also see the relationship between the baryon and dark matter and how the relationship could be quite complicated in the context of the sigma 8 tension. So people have probably heard of the sigma 8 tension in cosmology. It seems like the scale of clustering that you infer from high redshift probes, particularly at the recombination era, at the cosmic microwave background. The sigma 8 you infer from there seems to be quite different than the sigma 8 you would infer from a low redshift probe. So the scale of clustering seems to be a bit different. And so you could point to kind of exotic physics models, evolving dark energy, or exotic dark matter models to try and explain this. But one thing is that, again, we don't really fully understand the gas physics at low redshift. And trying to pick apart the gas physics from the cosmological input is quite difficult. And so one probe that I worked on is the Sunyaev-Zeldovich effect, which I quite like from the standpoint because it really shows these degeneracies. So the idea with the thermal Sunyaev-Zeldovich effect is you have photons from the CMB coming in. By the time they encounter really massive structures at low redshift, they're quite cold, these CMB photons are. But the gas is quite hot. And so you get what's called inverse Compton scattering, where the photon will collide with a high energy electron, and that electron will impart some energy. It will become Comptonized. And so here's a fun plot from the original Sunyaev-Zeldovich effect paper, back when you could draw hand-drawn figures and submit them to publications, where you see a very characteristic frequency shift. This is this imparting of energy that you see in the spectra of these photons. And so if we build up maps at different frequencies, different wavelengths of light, you can perform a subtraction and make a two-dimensional map of the Sunyaev-Zeldovich effect. These so-called Compton Y maps here. So those are the Compton Y maps from Planck. And you can, for very, very massive clusters, things like the Coma cluster, you can actually see very graphically the structure of this ionized pressure, the pressure of the gas, the thermal pressure of the gas. And so now we are interested in trying to model this effect. We're trying to relate these maps to the underlying cosmology and astrophysics. And one way to do that is within the halo model. And this is the most popular approach to try to model things like the power spectra of the Sunyaev-Zeldovich effect, where we model this map as the sum of all the halos that we're observing. So we're observing lots of halos over lots of masses. Each halo has its own pressure profile. The pressure profile could evolve over cosmic time, over redshift, as well as the pressure profile relates to the gas. And the integrated signal that we see is really the multiplication of these two factors, the halo mass function and the halo pressure profile. And so in the end, we end up with this integral expression where we need to sum up over the redshifts of relevance, sum up over the masses of relevance of these two factors multiplied together. And so quickly we see this degeneracy between cosmology and the astrophysics, right? We could change around the pressure profile, or we can change around the halo mass function and end up with the same integrated effect. Even when you look at each individual redshift bin, you could play the same sorts of games. So one question is, if we allow this pressure profile to vary, how would it affect the inferred parameter constraints? So you could build up these one-dimensional, one-parameter models to parameterize, say, the expulsion of gas from the halo, right? If there's some really hot process happening in a halo that's puffing up the gas, how would that affect our inference of sigma 8? And so here's just kind of a simple fit of that in the case of just trying to fit sigma 8 with omega, with this m critical. So this is essentially the scale that feedback processes could dominate, what scale it goes up to. And you can start to see that as you increase feedback, as you allow more and more non-thermal pressure to build up within these halos, you start to pick up this degeneracy direction. So while at no feedback, you can match essentially all those other low redshift parameters. As you increase the feedback, it kind of turns over, and you can actually also match the Planck constraints from high redshift. So the kind of question is, well, we could say that this is indicator of some kind of really strong feedback. How physical is that kind of model for really, really, really strong feedback? And the kind of question here is, can these simulations provide insight into these complex astrophysical processes? And this next video may or may not be broken. Okay, this video works. So here's a video showing a bunch of different astrophysical, cosmological, hydrodynamical simulations. This grid of hydrodynamical simulations was run by the CAMELS collaboration, where they took 5 different codes, ran them with lots of different parameters, try and understand how different ways that we model the feedback can affect the thermal history of the universe as well as the matter distribution of the universe. So the blue is the underlying, I think, baryon mass, and then the red here, the red colors are the thermal pressure of the gas, and just kind of showing how if you really want to turn up feedback to very, very strong levels, how it would affect this distribution. So for example, here you can see that while Ramses has some strong feedback at relatively high redshift, if you use the Simba implementation of the feedback, you get these really, really, really powerful feedback at late times. So to talk about hydrodynamical simulations, it's kind of nice to break down them into components. I'll say as a forewarning, I'm not a hydrodynamical simulation expert. And I'm sure there are some other people, certainly at this institute and probably in this room too, that are much more knowledgeable about the inner workings of them. But the way I like to think about hydrodynamical simulations is you have a dark matter component, you have a dark matter evolution you're trying to model. How does the dark matter move from the initial Gaussian random field to late times? You have the gas evolution. So similarly, you have a component that's evolving under gravity. But unlike the dark matter, it is collisional. So it does have thermal pressure and all the kind of standard hydrodynamical effects that you're familiar with. And then finally, the final thing you put on top is what's called subgrid physics. Basically anything that's not explicitly modeled under the gas evolution. So for example, star formation, if you had a super futuristic machine, maybe you could actually model the formation of stars jointly with the evolution of the cosmic structure. But at least nowadays, trying to do those jointly is pretty much infeasible. It's just such a huge separation of scales that it'd be quite difficult to do. So we run smaller scale simulations. You get insights from observations at low redshift to build something that you essentially inject on top of the gas evolution, the subgrid parameters. So the dark matter is, at least at surface, somewhat easy. You kind of have one equation, the collisionless Boltzmann equation, for the phase space distribution. This equation, although it looks pretty simple, trying to solve it analytically for anything that's at all complex is quite hard. And we're left to running n-body simulations. So essentially you have this phase space distribution, this F, that you're discretely sampling at early times. And you have Hamilton's equations to evolve it forward in time. And by Louisville's theorem, you can say that if you sample it enough and evolve it forward with these parameters enough, you'll be able to reconstruct the late time phase space distribution accurately. And while that's kind of simple on the surface, there's lots of tricks needed to actually do this computationally efficiently. If you're dealing with billions and billions of parameters, calculating the gravitational force can be quite complicated. Then we have the hydrodynamical components. So these are the Euler equations, or the Navier, a limiting case, the Navier-Stokes equations, where we are describing the evolution of the density, the pressure, and the momentum of the gas. And so while, again, these, like the collisionless Boltzmann equations, are relatively simple, actually analytically solving them, I think in the case of the Navier-Stokes equations, if you can even prove the existence of them, you win $1 million. So it's quite hard to solve analytically. And again, we have to discretely sample it. And there's different choices in how you discretely sample these equations. For the purpose of this talk, I'll be talking a lot about the Eulerian approach, where you're, rather than sampling them as discrete particles, you paint it onto a grid, and you're evolving the forces on the grid. And so in this case, the kind of the integration of this divergence terms end up becoming sums over the surfaces of each grid cell. And the important thing to know here is that in the end, when you discretize it and you're evolving the system forward, it turns the system just into a series of linear operations. Essentially, you're doing lots of multiplications by large matrices or large vectors to describe the interactions on the surfaces of these grid cells. The actual choices in how we break up these surfaces, how you calculate the flux over each of these surfaces can be quite complex, and I won't get into those kind of intricacies in this talk. But from these kind of approach, you can reconstruct, or you can try to construct this kind of standard cool hydrodynamical processes, things like fluid instabilities, or things like shocks that kind of give rise to the phenomena we see today in the modern universe. And then the final component is the subgrid physics. So this is, again, all the components that you can't quite describe or you can't quite exactly model with your Eulerian grid. All the exotic additional physics that could come from things like supermassive black holes, from the AGN formation, things that are happening really, really small. But those source of energy injection, as we saw in the first part of the talk, can really affect the late time observables, the cosmological probes, or these three-dimensional maps of the Lyman alpha forest. And so, yeah, so they could include things like metal heating and cooling. Some people prefer to group these into those Eulerian equations, things like star formation, AGN, cosmic rays, turbulence. There's a lot of choices in how people set up their simulations. And these choices do make quite a big difference. So there's a collaboration, the Agora collaboration, that was basically gave a little challenge to people who run these hydrodynamical simulation codes. Let's all choose the same initial conditions, say that we want to fit the same subgrid physics parameters, so the same metal heating and cooling, try to reproduce the same observed stellar mass functions and other probes like that. And even starting from those kind of simple rules, they could end up with very different late time evolutions of their code. So you can see here the gas distribution, the temperature, and the stellar components. Even starting from the same point, you get really different behavior. And when you dive even further in to try to reconstruct things like spiral arms of galaxies, you again see quite a variety of possible outcomes, even supposedly trying to solve for the same thing. So the kind of question comes up is, how can machine learning try to help this? How can we try to integrate these new machine learning techniques into hydrodynamical simulations, either to accelerate the hydrodynamical simulations, to try and add additional functionality into additional hydrodynamical simulations, or try to figure out essentially which one is right, which model is most accurate to our actual observed universe. So you probably don't need me to tell you guys that there's been a machine learning revolution. There's this collection of papers that was compiled by George Stein, who was a postdoc at Lawrence Berkeley National Lab when I was there, who ran off into machine learning. But this list has pages upon pages of various examples of applying techniques in machine learning to astrophysical problems. And I eventually got tired of screenshotting the pages, so I eventually gave up. And then, of course, nowadays we have ChatGPT to play with as well. But there's kind of a fun experiment you can try with ChatGPT, which shows the limitations of machine learning approaches. So here, ChatGPT has the functionality, you can generate images. You could try this also with other image generation programs. So I wanted ChatGPT to generate a picture of a wine glass filled to the brim, as full as possible. I'm sure everybody in their mind can think of a wine glass that full, right? But yet, ChatGPT spits out this. Here's my wine glass filled to the brim. And I'm like, no. I really want it to be better. It's only halfway filled. I want it all the way filled to the top of the glass. And this is what ChatGPT thinks is filled to the top of the glass. And then I'm still bothered by it. I say, no, I want it only filled halfway. Sorry, it's only filled halfway. I want it filled literally overflowing. And this is the picture it generated, where this brim still not filled to the top. It's weirdly sweating wine out this way. It's giving me complete garbage, right? This is not a realistic picture of a wine glass. Where's the wine even coming from? It's not overflowing off the top. And this is because, right, the ChatGPT only sees the images that it was trained on. It's fundamentally limited by that training set. And if you go on the internet and try to find pictures of wine glasses filled to the brim, it's not a very common thing, right? Nobody pours wine all the way to the top. You pour beer maybe all the way to the top. but wine, you don't do that. And so because of that, ChatGPT doesn't have that in its training set. It can't create this whole new thing out of thin air. And we'll see this kind of come up again and again as we look at machine learning in astrophysics. So for those who are not yet hip and with it with neural networks, the way I like to think about neural networks is it's just a fancy linear regression. If you know how linear regression works, you know how ChatGPT works. You know, maybe a simplification, but it is at a certain level, I think, accurate. So in a linear regression, you can kind of draw a computational graph for a linear regression like this. You have some input vector, x1, x2. You multiply them by some, what we'll be calling here a weight, but the slope of your linear regression. Add in a bias, and you get out your output. And then if you're fitting a linear regression, you just fit to figure out what weights and what bias best fit your data. This is, I guess, high school or college level stuff. And so when we go to make a neural network, let's just make a simple one-node neural network. We just add on an activation function. In this case, I'm showing a logistic regression. Logistic regression, we take a linear regression and add on a logistics function. Basically convolve the two together. And so this is a simple one-parameter neural net or one-node neural network. And so when we go to more fancy neural networks, things, even going up to something like ChatGPT, it's essentially drawing a similar picture rearranged various ways. So we could draw a shallow neural network, so just combining together neural networks. The formula ends up being quite, relatively simple. Then, of course, it gets more complex as you go into deep neural networks. You're layering together more and more of these nodes. And so essentially the idea is to try and capture more and more of the nonlinear structure of the data with this deeper neural network. And so then when it comes time to actually training this, it goes to the field known as differentiable programming, where we want to make we want to be able to take derivatives essentially through our models, try and perform inference on the parameters. In this case, for a neural network, we're just trying to fit the most likely or the best fit weights and biases. We want to find what values of W and what values of B match the data given some set of training data. And so the way that works is essentially we are able to write down some objective functions. This is like a mean squared error type loss function. You're trying to fit for identifying handwritten digits. So you want to make sure that the predicted digit matches your training set of predicted digits. Then you can look at the derivative of this objective function, of this likelihood function, and perform a gradient descent to figure out how to update the weights and biases. You perform this iteratively over time, and you can figure out what the parameters are of your neural network. And along kind of the way that these networks have been developed have also been expansions in hardware that have made training these types of neural networks quite efficient and quite fast. In particular, development of graphical processing units, which have been all the rage now. If you look at NVIDIA stock shooting through the moon, maybe not the past few weeks, but over the past few years. Wish I bought it a few years ago. Anyway, so the GPUs, though, are very good at very fast vector operations. Is kind of the lowest level thing. If you have something that can be written down as a set of linear operations, it is likely that you could implement them quite quickly on GPUs. Things that are more tree-based structures, like if you're building octatrees and all these kinds of things, they may or may not be as efficient. But for things that you can write down as vector operations, it's quite efficient. And so here's an example where I quickly did a benchmark test of a dark matter evolution code that will pop up later in the talk. JAX PM. You can see that the CPU and GPU have somewhat similar asymptotic behavior. They kind of have the same slope as you increase particle number, but the starting point for GPUs is way, way, way better. So something that takes literally only a couple seconds on a GPU could take minutes, if not hours, on a GPU. So when we look at the role of machine learning in astrophysics and cosmology, you could set things up various ways. In the same way you can connect neural networks various ways, you can try to connect the neural networks to our inference various ways. So one thing you could do is you could try direct regression / inference. We have all these hydrodynamical simulations, we have all this data. Can we just combine the two together to directly infer what our parameters are? And I would say you have to be kind of careful with this kind of thing. As we saw in the ChatGPT example, if there's something in the data that that the model is not trained on. If you have the cosmological equivalent of a wine glass overfilled, it will spit out crap, right? It will not train very well. And I looked at this in the context of adversarial attacks on neural networks. So if people are interested, they can ask me more about that later. Some things that I think are slightly more interesting is trying to use ML techniques to generate additional simulations in a really rapid way and be able to apply traditional techniques on those new simulations. So right now, we're limited by how many hydrodynamical simulations we can run at certain volumes. Can we train neural networks to be able to generate more of those train neural networks to generate more of those simulations over larger volumes efficiently, to be able to run full cosmological analyses on the actual hydrodynamical simulations, not have to paint on baryons with approximate ways. And then in the final part of the talk, I'll discuss some of the kind of integrated approaches to leverage these machine learning techniques within simulations in an integrated approach. So for the surrogate model approach, I guess I'll be somewhat quick here since I don't have too much time. So the idea with a surrogate model is you have a simulation that's relatively easy to run. So in this case, I'll be talking about dark matter only simulations. So ignoring the gas component and ignoring the subgrid physics component. And we want to map this dark matter component to the full hydrodynamical fields. And so we can, of course, use machine learning for this. This is a whole field in machine learning called image translation, where you can take pictures, say this is like a picture of a horse, I want it to be a picture of a zebra instead, and the machine learning model will know how to map between it. It sees lots of pictures of horses, lots of pictures of zebras, it can figure it out. Similar with these ones mapping summer to winter. But there's lots of different ways to do this. So one thing you could do is you could take a deterministic approach. So I have one dark matter simulation, I want it to be mapped to one hydrodynamical simulation. And that's this deterministic approach. You could also take a variational approach. Because of uncertainties in the hydrodynamical simulations, because of uncertainties in the underlying gas physics, there could be many different possible hydrodynamical simulations that can all be mapped to the one same dark matter. That could all correspond to one dark matter simulation. And the final one, which I don't think I'll have time to get into, is to actually combine these two approaches with modern diffusion networks. But for the deterministic approach, you can imagine we have these neural networks. They're really good at predicting something. We can just feed in lots and lots of matched pairs of dark matter simulations and hydrosims, say, can you make a model to best connect the two? And with these tinkered toys neural networks, you can come up with lots of different architectures. One popular one from image translation is these UNet structures, where you take some image, you pass it through a few layers of neural networks, and then you downsample it. Pass through a few layers, downsample. Pass through layers, downsample. Pass through layers, downsample. You have this, what's called a bottlenecked layer, and then you do the same thing in reverse, upsampling, but combining at the different scales. And so this UNet structure is designed to try and capture correlations between different scales. We think that there's a connection between the large-scale structure and the small-scale hydrodynamical physics. Hopefully this network can capture it. And we're outputting the hydrodynamical field, so the baryon baryon density, velocities, and temperature. And finally, we're going to map that with traditional techniques to the underlying flux, Lyman alpha forest flux. And here you can see an example of this, where we have the input dark matter fields and the velocities, the output Lyman alpha predicted field. We can look at the Lyman alpha true field, and we find a really good match by eye. And you can go deeper into it and match the summary statistics too. We find that we're able to reproduce the Lyman alpha forest power spectra and PDF quite accurately. So with this type of approach, you could train it on relatively small Lyman alpha forest, relatively small hydrodynamical simulations, but run it on huge dark matter only simulations. You can also look at this as a variational approach. So rather than just mapping it to one, we can map it to many different hydrodynamical simulations, introducing a latent space to try and capture the uncertainty in this mapping. So this turns into what's called kind of a Bayesian method for it, and you're able to actually look at the uncertainty in the maps. So we can look at the ensemble of possible maps and figure out where the models most certain of the outcome and where the model is least certain of the outcome, and try to propagate those uncertainties to the end statistics as well. So going back now to this field of differentiable programming, can we use these techniques from machine learning that were developed, this automatic differentiation, these constructions of computational graphs, can we use these to do a whole new type of inference without having to resort to training a neural network, right? There's a lot of issues. Maybe it's not robust. Maybe, maybe our actual data is quite different. But can we try to infer new things by deploying automatic differentiation? And so to kind of go a little bit deeper into what automatic differentiation is, you can imagine we have a simple computational graph here. So we have two inputs, x1, x2. We have a simple function here. You can kind of imagine this is breaking down the computer programming into each of its individual steps to try and figure out what the output of this function is. This is called the forward pass, so the forward primal trace, if you're feeling more fancy. And so what we do with automatic differentiation, there's two different ways to do it. There's a forward way and a reverse way. I'll talk about the reverse way here. But essentially, we look at if we change this last component, this output of the model by 1, how does that affect the inputs at fixed input values? So you can actually use multivariate calculus tricks going back down this graph, trying to figure out how do the inputs change. And so now you can imagine if we have the output as a loss, of like the loss of our model, the thing we're trying to optimize for, we can actually figure out how do we change around the inputs to best match the outputs. How do we best fit our data, our model to the data? So this is what happens with machine learning models, where we're changing around the weights and biases. But here we can actually also look at it in terms of the input. And so we can rewrite our cosmological inference as trying to optimize for the initial phases, the initial density, given our observed late time data. So in the context of cosmological hydrosims, we have to kind of look at all these different components, the dark matter, the hydro, as well as the subgrid physics. The dark matter has been kind of the thing that people have most worked on in this context of trying to do this kind of field level inference. There's been a whole little industry developed of all these codes using CPUs and GPUs implemented in every machine learning language you care about. So if you like TensorFlow, there's one in TensorFlow. I've become a big believer in JAX, so there's one in JAX. I think there's some stuff in Julia too, if people like Julia. And what's really great about these models, particularly the more recent ones, is it's quite simple to write down the differentiable framework. Because it's all these linear operations, there's a lot of commonalities. There's been whole libraries developed. So you can run a whole dark matter only simulation of the universe with, depending on how you break it down, 12 or even like 6 lines of code to actually output a final density field. And you can then go back and take the derivatives through this to figure out what the initial density field is. So to give an example of this inference of the initial density field from Lyman alpha forest, these tomographic maps end up being a really great place to deploy these methods. The high redshift universe is quasi-linear. It's not, you're looking at scales of megaparsecs at redshift 2, so there's not crazy densities you're trying to reconstruct. It's, for the most part, diffuse. And so these optimizations can be quite efficient. And so the particular method that I've worked on over the years is this TARDIS method, where we have some initial density field. We evolve it to a late time density field using those packages we saw before. We paint on the hydrodynamics. This is the kind of big question mark that we later on will try to refine more. We map into the data space, so we look at the actual X, Y, Z positions of the data and try to figure out what the initial density field is. So here's an example from a mock made to look like the upcoming prime focus spectrograph survey, where I'm involved in the galaxy evolution component, where we have the initial density field, the late time density field of the mock, and we're trying to reconstruct the initial modes, the initial Gaussian random field, given some Lyman alpha forest data. And we find quite good accuracy depending on how good the projector color is. But you can see here, there's big clumps, voids. And you can actually compare this to traditional methods simple Wiener filtering, the connecting the dots method, and you can create, and you have significantly better reconstruction quality. And so we applied this technique to the Clamato field that I talked about earlier to create the initial Gaussian random field that gave rise to the late-time universe. We can actually run hydrosims from those initial conditions and find that other than these extremely massive clusters I talked about earlier, you actually get really great results from the hydrodynamical simulations. You find galaxy overdensities where the Lyman alpha forest predicts there'd be galaxy densities within this framework. But again, this all kind of seems a little bit backwards, right? I use these dark matter only models to try to reconstruct the late time universe. But we know those dark matter models, dark matter only is not a great predictor because as we saw, there are these clumps of neutral hydrogen that don't match the galaxies. So can we try to really disentangle the hydrodynamical effects from the dark matter effects? Can we really try to see where this feedback comes from? And this motivated this idea of trying to actually backpropagate not just through the dark matter only simulation, but the full hydrodynamics. So this leads to the final topic here of fully differentiable hydrodynamical simulations. So the idea is that we could write down our Euler equations from before. Here's kind of a simplified version, our friendly blast waves. We can actually try to implement the solving of these equations in a differentiable framework. So within one of these deep learning packages. In this case, I used JAX. I like JAX. This is actually based on, the first thing I looked at was Uli's old hydrodynamical simulation codes from the late 90s, early 2000s. And it was a nice way to understand the physics, because again, not an expert on the hydrodynamics. And we can find, so let's imagine we have these blast waves. We have the late time field. Let's try to reconstruct the initial conditions. And so here's this optimization showing we have this target field we're trying to figure out the target field of. We run the hydrodynamical simulation every step. There is the counter. And we can find within 10 to 100 steps, I guess around 50 steps, we actually have a really great reconstruction of the predicted field. And this particular problem is quite hard because there's a lot of degeneracies, right? You could have blast waves moving in or going out. And so it's hence why you kind of get these interesting features on the outside as the reconstruction progresses. But with this type of approach, you can make cool animations like this. I make a new animation whenever I go to a new place. And so in a few seconds here, you'll see a hydrodynamical simulation where you have the initial conditions that give rise to type A. And you can even parallelize this to many GPUs to make higher resolution. So here's a hydrodynamical simulation where I optimized to find that it gives rise to. This one's a little bit too long. I need to shorten it. Yeah. Change around the frame rate. Making these animations is always a pain because you get a great result. And you're like, now I need to make a cool animation to show it as well. And here it's also type A, just with the more with traditional characters. With more GPUs, you have higher resolutions. So you can make the traditional rather than the simplified. And now finally, we can do what we really are motivated by, which is coupling it to the dark matter. So we can actually jointly evolve, basically plug in one of these existing particle mesh routines with the hydrodynamical simulation, evolve both fields jointly, and then backpropagate through both fields jointly to actually try and reconstruct the large-scale structure, the initial conditions of the large-scale structure with the full hydrodynamical evolution. And so here's kind of a toy example. It turns out backpropagating through that earlier example, although it is possible, it takes a very long time without further optimization. So here's just a toy example to show it. So we have some noisy data. This was kind of meant to be fake TSZ type data. So a fake, like a noisy 3D map of the thermal pressure field. So we added in Gaussian noise. And so here we can actually try to, again, try to do the same type of optimization. Where here's the true initial conditions. Here's the true late time energy field. Again, jointly evolving the dark matter with the baryons. And we try to match this data. And we actually find within a fairly small handful of simulations, within 50 or so simulations, we have a pretty accurate representation of the late time energy field, as well as good qualitative match between the initial conditions and the reconstructed initial conditions. So kind of the dream here is that with this type of framework, combined with some smart people who are better at implementing hydrodynamical simulations at scale, we could try to do full field level inference of all observables down to redshift 0, marginalizing over all subgrid physics, all these secondary anisotropies. You can try to just throw everything into a big pot and reconstruct an actual simulation that matches our universe. Essentially what we tried to do with the Clamato field in that small region, try to do it at scale for all cosmological probes. Of course, that's quite futuristic. Maybe if you have a few million GPUs to throw at me and I can use them for a year or two, I can figure out how to do that. But the more near term is you could do the same, you could try to do a similar thing, but rather than work in the full initial condition space, you could just try to figure out what parameters would give rise to certain summary statistics. So rather than trying to optimize for all initial conditions at once, you could just look at the parameters of the model. So you fix the realization and try to just figure out the parameters. So this would allow you to basically interpolate between cosmological and astrophysical parameters within a joint framework. So one thing we need to do that is we need to include subgrid physics. So this ends up, in this first work, we just looked at a toy model where if you're above a certain density and below a certain temperature, you have cold, dense gas. Those regions could collapse to form stars. And here we just allow the star's energy to be released at once. So this is a 4-parameter model. You have the probability scaling. So what's the probability that in a region that satisfies these two conditions, you have stars forming. You have the two condition parameters, the critical temperature and critical density, and you have the energy that's released. And so you can imagine this is a stochastic process that we'll be back propagating through. And so here's an example of doing this. As you can see, I really like explosions. So it's fun to kind of turn up the subgrid physics to a really high number just to show that the numerics work out. So here you can see all of our supernovae are blowing up. So like probably a factor of 10,000 times more energetic than real supernova, just to show that you can back propagate through these kinds of physical effects. And you can then run Hamiltonian Monte Carlo. So you can actually run gradient-based methods to try and figure out these parameters and reconstruct the joint parameters in both the cosmological parameters as well as the astrophysical parameters. So this would be something that would be very inefficient to do without the gradients. Gradients allow you to explore this space quite quickly with gradient-based methods. And so we're able to reconstruct these parameters from mock data. And so in the future, there's a lot of other kind of, this opens up a whole new doors into how we run hydrodynamical simulations. Right now here I was trying to implement a standard hydrodynamical simulation within a differentiable way. But when we're able to back propagate through hydrodynamical simulations, we could include machine learning models as part of it. So one kind of example is, let's say we have some high resolution simulation. So here I have this Kelvin-Helmholtz instability with all these pretty swirls. You can run the same one at low resolution. Here, low resolution was just shown as with lower pixel resolution. You could also imagine this as fewer time steps with fewer physics implemented, without adaptive mesh, with all these kind of things you could add onto hydrodynamical simulations to make them more accurate, but very computationally expensive. So we can imagine running two simulations, one with low resolution, one with high resolution, and figure out how do we augment the low resolution one to match the high resolution one. And just taking the snapshots at late times to do this would be really computationally difficult. But we could instead do it in an integrated fashion. So this is this idea of a augmented low resolution simulation. So you can imagine we could take some initial condition field, we pass it to the high resolution. So this could be a standard hydrodynamical simulation, your favorite hydrodynamical simulation of even for astrophysical objects. You could do the same thing for example, for AGN disks or for globular clusters. Then the same one you pass the low resolution simulation. This will be basically some version of the hydrodynamical simulation that I was showing, the differentiable hydrodynamics. And then you do a standard low resolution step, but then you apply a neural network augmentation. Low resolution step, apply neural network augmentation. And the same thing all the way to late time. And the idea here is you can then back propagate through. Here you have the same model at every step, and you can actually fit those parameters. And you can minimize the loss over all the time steps jointly. And so this can provide a framework for example, let's say there's some subgrid physics parameter that we don't know how to model, that is not currently modeled in existing hydrodynamical simulations, but maybe is out there in the real world. We can actually figure out what form those kinds of subgrid physics parameters would take. Or alternatively, you could say, I want to run this hydrodynamical simulation to encompass the whole DESI volume, right? That would be super expensive computationally to implement at the resolution necessary. But it's possible with this type of approach, you could actually augment a lower resolution simulation to actually capture those small scale physics effects. So this is an approach I'm quite excited about. And all of these kind of approaches I'm hoping to implement into the very soon upcoming, I think we're taking data in the next week or two, over the next couple of weeks, for the prime focus spectrograph, and in particular for the galaxy evolution component. So I mentioned earlier this Lyman alpha tomography that we're doing at, I guess here it's intermediate redshift. I call it high redshift, but redshift 2. There'll also be a low redshift component at redshift 1 and a high redshift component at redshift 6 to 7, where we're trying to understand the evolution of the gas and the galaxies in its cosmic environment. And so these types of field level frameworks can provide a unified approach, a unified modeling approach for all of these regimes. So with that, I'll leave up my summaries and take any questions people might have.
Do you have any results for low to high?
So no, so these ones are, yeah, this is very futuristic. I have not yet implemented the thing. So this was inspired by some people who are looking at a comparable approach for weather modeling, where they're looking at very different types of physics of like a cloud formation, and then apply the kind of physics of cloud formation to large scale, like Earth level simulations. They found they were able to get quite accurate predictions of like where a hurricane would go, for example, with this type of approach. And so the plan is trying to apply those types of methods to hydrodynamical simulations.
You can do that for n-body simulations as well, I guess.
Yeah. So there was some work done to basically augment, so going back to this, maybe I need to go too many slides back. Yeah, so these Hamilton's equations for evolution, the calculation of this G, people have looked at basically, there's different ways to calculate the force. You could use a mesh-based method or a particle-based method. The mesh-based method approximates the small-scale interactions. And you could actually augment the mesh-based result with a neural network within this type of framework as well, and get better force calculations. Oh yeah. Oh yeah. Over there.
So can you explain more on the differentiable part? Because I can imagine, for example, for subgrid models, there are some pre-parameters that you can try to find an optimal set of parameters. But for n-body simulations and also for the hydro, I think everything is deterministic. So what are the three parameters that you're trying to optimize?
Yeah, good question. So the idea there is the free parameters we're trying to optimize for are these, for most of the examples I was showing, was this initial density field. So you're trying to optimize for the full 3D grid of the initial conditions of your simulation. So this will be in abstract, whatever the resolution of your simulation is. So if you're running like a 1024 cubed resolution simulation, you're optimizing for 1024 cubed parameters. So yeah, very high dimensional optimizations, but these types of optimizations are quite common in machine learning, because if you look at something like ChatGPT, you have, I don't think anybody knows exactly how many parameters they have, but it's in at least the hundreds of millions, if not billions of parameters. So they're doing the same type of optimization, back propagating through these computational graphs. But for them, it's these neural network components. And for us, it's the linear operations of the force calculation or the flux calculation on the boundary of the hydrodynamical simulation.
So the goal is to get a late time snapshot density distribution and infer the initial condition.
Yeah, exactly. Yeah, so you could take your, so yeah, for example, in this case, the data that we take are like these Lyman alpha forest measurements. So to get the Lyman alpha forest measurements, like if we're making a mock for Lyman alpha forest, you run a hydrodynamical simulation, you pick out lines of sight, and that gives you the Lyman alpha forest simulation. So here we do the same thing. We run, in this case, a dark matter only simulation, paint on the Lyman alpha forest, and get out the those one-dimensional lines of sight in the same spots as our actual data. So you can make a one-to-one comparison at the pixel level. Yeah, I guess over there.
Regarding that comment, so then does that training depends on which hydrodynamical simulation you are trained on?
Yeah, so for this particular example, I'm basically separating out the dark matter component with the gas component. So in this case, particularly back in here, I wasn't thinking about running the fully differentiable hydrodynamics. It was just, we can run the dark matter, and then we can paint on top with a bias model our hydrodynamics. So here, I'm just using some kind of analytical mapping. It's an exponential mapping of the dark matter to get the neutral hydrogen. But yeah, in general, the parameters you would fit there would be dependent on what simulation you're training on. But then in the fully differentiable hydrodynamical case, you're not fitting any parameters or anything. You're not comparing it to, you're not training a neural network or anything like that. You have some actual physical parameters that describe your subgrid physics, and you'd be fitting those parameters jointly. So in that case, for example, the star formation case, you'd be fitting the initial condition field plus that energy scale of the supernova or the critical density of the star formation, or how much energy an AGN injects into its environment. However you decide you want to break apart the subgrid physics model.
So is it right to say that there still remains some sort of degeneracy between initial condition and the model, how you model the baryonic physics or subgrid physics?
Yeah, I would probably say so. Like the hope would be that this type of framework allows you to combine basically every single probe you can imagine. Any probe that is a function of some hydrodynamical simulation output, you can include jointly. So although I don't show it in this framework, we also did joint Lyman alpha forest galaxy field optimizations to see how well that shakes out, finding, at least in the context of the hydrodynamical simulations we had mocks for, we found really good reconstructions with that joint thing. And there's, the sky's the limit. You could do everything jointly together. And yeah, there could still be some, uncertainties in the hydrodynamics versus the cosmology. But the hope is that, doing everything jointly, you can pick apart it enough that it's not a concern in the end. Yes, back there.
Okay, thank you. This is interesting talk. So I've been trying to look into this sort of machine learning methods, and one thing that makes me always wonder about is that it doesn't seem to be still very good at handling anything related to non-linearity.
Sorry, which thing is not very good?
Non-linearity, like hydrodynamic speed.
Okay, sorry, related to which topic? I didn't hear the.
Generally speaking.
Oh, sorry.
Generally speaking, I'm working like MHD hydrodynamics.
Oh, MHD. I see.
And when I'm looking at these AI and methods,
I see.
seems to be often that at least things get non-linear is difficult. Do you have any thoughts about that? I mean, this is very big question.
Yeah. Like it's certainly, it's so problem specific, and I'm sure there's a lot of people who are who have other opinions about it. Kind of like when I was showing this thing here, these different steps. We were kind of going through different neural network model implementations. This was like a UNet with some adversarial loss. This was a VAE approach, a variational autoencoder approach, and this thing worked pretty well. You could look at this paper and see pretty figures where I chose whatever makes it look the best. But I was still not quite happy enough. So that motivated moving on to the next greatest thing, these stochastic interpolants. And so far, I've been really blown away by stochastic interpolants and kind of diffusion processes in general. I don't know which thing you've been playing around with so far, but I think it's definitely worth looking at that. I found, yeah, like when I was looking at like stellar component, like mapping from dark matter to stellar component, which is really, really, really nonlinear, it did quite well. You know, when I'm moving on to something like a disk or something like that, if you're looking at like MHD on that type of scale, I don't really know. It's probably quite hard. That's also one of the cases where these kind of integrated approaches might be better, because you could solve the MHD equations directly. That provides, you know, a big step into the nonlinear regime, and then maybe you just need to do a small correction on top to include something that you can't make differentiable or something that's too computationally expensive to make differentiable. That'd be kind of the idea there. Yeah.
Maybe adding to that, I'm thinking why that is the case though, because like even if you are using UNet, you will add non-linear activation, right? So shouldn't essentially it should be able to at least model some linear physics?
Yeah, like there's nothing fundamentally that makes these things not able to handle the nonlinear physics. There's this, like all of machine learning is based on this universal approximation theorem, which is this thing from math that like basically any nonlinear function of arbitrary complexity can be modeled by something that's essentially like this, repeated over again. But you know, even though it can be mathematically proven it's approximated by this function, actually solving this function, actually doing that optimization, can be quite difficult and quite difficult to get good results with. And, you know, you have a limited amount of memory in your GPU. So those things both combined together can make these types of tasks harder than they appear at first. But it's true, that's kind of the most simple nonlinear things. Like for example, if you want to map from like initial conditions to late time density field, doing like a UNet for that, that's really, really good. That type of nonlinear structure, kind of the classic nonlinear structure, is really, these machine learning models are quite good at. But then when you go to something that's stochastic, or something that has really non-local effects at the level of the maps, something like a big thermal bubble, a big shock around like a forming cluster, those things, then you kind of get into the nitty-gritty of it, and a lot of these problems will pop out.
I think we can ask, like you can ask more questions after the podcast is over. I think
Yeah, I don't think I have any meetings after this, so.